Hello everyone. In this video we are going to talk about one of the approximations called Padé approximation that is very important and useful in controls. So this is very useful when you have system with delays. You know from Laplace transform that Laplace transform of a function that has been delayed for t seconds is the Laplace of the original function times an exponential function like e to the negative ts. And this extra exponential that is multiplied by this transfer function, which for physical systems, this is typically your rational function, right? There is a numerator and a denominator, some polynomials. This extra exponential term will cause some problems for analysis. But before that, before we talk about analysis, simulations, design of control or anything, let's look at the effect of this delay on the response of the physical system. So of course, in the time domain, if you have any transfer function, like let's say this one, and you draw the step response of that, so this is the step response, you see an underdamped response for the system G. And then with the transfer function, you can add an extra option called input delay and give it the amount of delays in seconds and create a delayed version of the system and then plot the step response of that on the top. And you see that here clearly the response of the delayed system is exact same thing as the original system, but with what? With 2 seconds delay in between, right? In the frequency domain, on the other hand, the effect is what? We know that this exponential term, right, if you replace for sj omega, this is going to be e to the negative tj omega. And you know the magnitude of this guy, if you call it, let's say, z, right? The magnitude of z is 1, but the phase of z is negative t times omega. So clearly it's not going to affect the magnitude, but it is going to add a negative term that is linearly increasing with omega to your phase, and that's what you see here, that you see the magnitude of the original system and the system with delay are on the top of each other, but in terms of phase, you see that the phase of the system with delay is constantly decreasing. Okay, so this is in terms of what? In terms of phase and the frequency response and the time response domain. Now you might say, well, can I just ignore the delay and still go ahead and treat the system as if there is no delay? So ignore that delay, ignore that exponential term, and go ahead and analyze the system and design a control for it? The answer is no. And you can kind of see why, even just by looking at the frequency response. When you move one of these curves, the phase and the gain margin will change. And when those change, the relative stability of the system would change. Here, in order to explore that, I show you one transfer function, and then another transfer function with, again, 2 seconds of delay, the same transfer function, but 2 seconds of delay. Then I'm gonna use a unity feedback on both of them using the command feedback, and then I apply the margin command on them, so it shows the phase and the gain margin, right? So I put G and the delayed version of G, I put them in a unity feedback system, and then I will look at the stability of the closed loop system. Okay, so the feedback transfer function h here is 1. And the other time I put gd instead of g. And if you look on the left for g, you clearly see that the original system closed loop is stable. You see phase margin is positive 53 degrees and gain margin is infinite, right? So it's completely stable. But if you put GD in that unity feedback system, now take a look. The gain margin is still positive, which is good. Of course, it's reduced from infinite to 18 decibels now, but your phase margin is negative. And negative means the system is what? Unstable. So you see, I did the same control design, very, very simple, unity feedback, and one system was stable, the other one was not. So delay is not something you can ignore, okay? It is going to affect your simulation. It is going to affect your control design. So now the question is, well, can I go ahead and use the tools I learned in classic control for analysis and design? Can I go ahead and use them while my system has this delay? And the answer is, if it's for the Bode diagram, yes, the Bode diagram can handle what? Can handle your delayed system that has this exponential term. But unfortunately, if you try to do a root locus for the system with delay, or you try to design a LQR controller, right? You want to do any optimal design or anything, even robust control, the commands that you have over there, they are not going to work, okay? So if you want to see, just go ahead and type in this command rlocus for that GD, and you're going to see that MATLAB is going to give you an error and say, hey, sorry, I'm not going to be able to work with that. And here, let me show you that. So here I create the system with delay, as you can see, and all I need to do is to say rlocus of GD, right? And look here. You see, the rlocus command cannot be used for system with delays. Use Padé command. And this is exactly what we're going to discuss. What is Padé? So Padé is an approximation to this exponential function, but this approximation is going to look like your f of s. It's going to be a rational function with the ratio of two polynomials. So the approximation would look like another physical system, and then when you multiply them together, still you're going to have a physical system and you can analyze it. Now, keep in mind it's an approximation. It's not going to be exactly equal to this exponential, but we're going to see when is it that it's good, how we can make the approximation better, and so on. So first, let's look at this Padé approximation. What is it, and what is it that we can do? So there are different ways to approximate an exponential with a rational function. One of it is the Taylor series, and the other one is Padé approximation. And Padé approximation is typically the one that is used in control system. And what is that? The goal of this Padé, as I said, is to replace your exponential with a rational function of two polynomials. Now, in general, the Padé approximation is what you can see here. Two summations, two polynomial terms, one in numerator, one in denominator. And the important thing is to find these coefficients P and Q, okay? P and Q, the coefficients of the polynomials in numerator and denominator. If you find them, that's it. That's all your Padé approximation. And you can do it by hand. You can use the formulas provided here. You can look up the tables, or you can use the Padé command in MATLAB. There are all different types of methods that you can apply that, okay? I can show you all of them if you want. First of all, while the order of the numerator and denominator in general can be different, one can go to order m, the other one can go to order n, we always choose the case that m and n are equal. So we choose the same order for numerator and denominator, and you might say, why? Why don't you use a case that m is less than n, right? So it's like a physical system. It's a causative system. Well, the reason is this magnitude that should not change. Remember, the delay does not change the magnitude. And you can show that when you have polynomials, only if the polynomials are of the same order, then the magnitude is not going to change. Okay, otherwise the magnitude is going to be affected significantly, okay? And that is quite obvious in terms of when omega goes to 0 or when omega goes to infinity in these ratios, how you would see the ratios are changing, right? So clearly you see here when omega goes to 0 or s goes to 0, this is the Padé approximation when both numerator and denominators order 1. You see that the ratio is 2 to 2, which is 1. When omega goes to infinity, again, you see that the ratio is like -1. So the magnitude is not going to change. Okay, the magnitude ratio is going to stay at 1. Okay, so that's why we use m and n to be equal. So this approximation when you multiply it by the physical system, it's not going to what? To affect the magnitude of the system, just change the phase to present this kind of behavior that you see over here. So that's first thing. Second, how do you find this P's and Q's, these unknown coefficients? How do you find them? Well, there are so many ways. One is there are formulas for them that you can see here. These formulas for P and Q, the numerator and denominator coefficients. You can use them based on the factorials of n and I, or you can look up tables like this, which are showing for degrees 1, 2, 3, 4, 5. And here you can see the parameter t is involved, which is the delay in seconds. So you can use that one. You can use the MATLAB command. MATLAB command also taking advantage of these formulas. And we're going to see that. So you pass to the Padé command in MATLAB the delay and the order that you want for both numerator and denominator, and it gives you the coefficients of the numerator and denominator, so you can use the TF function or transfer function to create the physical systems, this command here. You can also calculate it by hand too, but to save the time, I'm not going to go over that, but basically that's calculating this Taylor series, okay, for e to the negative ts or Maclaurin series, and then using terms from the constant term all the way to the term that the power of the polynomial is m plus n, or the order of it, and set that equal to the Padé approximation with some unknown coefficients, right? So in this case, basically, if we want order 1, let's say m and n equal 1, instead of that 2, this 2, and that negative and positive t, you can use 4 unknown coefficients, then set it equal to the Taylor or Maclaurin expansion of e to the negative ts up to the order 2, which is m plus n, 1 plus 1. And by setting those polynomials equal and finding the unknown coefficients, you can find formulas like this, okay? But here, we're gonna save the time and not go over that one. So this is how you can determine these coefficients, or as I said, we can use MATLAB, which I'm going to show you right now. So now the question is this: what order is appropriate? Now that I know, I can find them, now that I know m should be equal to n, which one of these n's is appropriate? The first thing I need to show you is the higher the n, the better the approximation. Okay, it's like a Taylor series or Maclaurin series, right? The more terms you use, the better the approximation. That's the same with a Padé approximation. As you can see here I have a pure delay of like 5 seconds, and then as I add basically higher terms, right, for Padé, you clearly can see that they are trying to get closer and closer. Of course, there is going to be more oscillations in the time domain, right? But ultimately, it's like a Fourier series kind of, right? Ultimately, they are trying to get to this. And, or if you look at the frequency response, this is more revealing. If you look at the frequency response, this plot that I generated and I show you, you can see that with higher orders, the range of the frequency over which the approximation is overlapping with the original system is getting what? Bigger and bigger. So in this case, in this system here, this dark blue curve is the original system for, let me show you the code. So here, what you have is, you have the pure what? You have the pure delay, a system with just delay, and the delay is 1 second. So you create that system, and then you create the phase plot for that system. So here I'm not using the entire Bodhi command. I'm just using the Bodhi command to give me the magnitude and the phase, and I only plot the phase. Now here I'm doing a couple of other things before I do the phase plot, which I want to explain it to you. One is this W out, which it gives you, I don't need. Second, I give it my own range of frequencies here from 10 to the negative 1 to the 10 to the positive 1, 100 data. The second thing is, when it gives you the phase, the Bodhi command, the phase that comes out of the Bodhi command has 3 dimensions. So in this case, the dimension is 1 by 1 by 100. and I cannot plot that versus this frequency. So the thing I need to do is this command squeeze, which gets rid of one extra dimension. So it converts my phase, which is 1 by 100, it just converts it to 1 by 100. So it gets rid of one extra dimension of 1. The other thing is the initial phase, because of some numerical calculation inconsistencies, if you don't subtract the original phase from the phase and plot them, what you will see is instead of all of these curves having the same value at very low frequencies, you see that as the order goes up, the amount of phase keeps going up. But what it is just a 360 degrees plus the original phase. So for example, if the phase of the original system is, let's say, -1 degrees, then the phase of the first order Padé approximation is -1 plus 360, which is like 359. The angle of the phase of the second order system is -1 plus 2 times 360, and so on and so forth. So all of those angles are the same practically, right? But first of all, do not use the mode command, the modular command, because it creates some oscillations in your plots. I would subtract the initial phase from the phases so I get a consistent plot, and that's what I did. So this is the original system, and then here for orders of 1 to 5, I found the numerator and denominator with the Padé command. I formed the system with the transfer function. I got the phase out of it. I plotted the phase on the top of the original one, and then I added the legend, right? So once I run this code here, I will get that graph. And again, if you look at this graph, you see that, for example, the system order 1 is only matching my frequency, my original system, my delayed system, up to what? Up to about 1 or less than 1 radians per second. If I add it to order 2, now system of order 2 up to 2 radians per second or so, it is overlapping my system. The order 3 goes to 3.5, the order 4 goes to maybe 5.5, and the order 5 goes all the way to 7 radians per second. So the more, as I said, the higher order that I use, the closer my approximation is to the system. But you might say, what's stopping me from using bigger and bigger orders? Well, the thing is this. There are limitations to this. One is Padé approximation, as you saw, is good at low frequencies, right? You clearly see at low frequencies, the approximation is matching the original system, the one with exponential. At higher frequencies, it's not showing itself, okay? The gap is going to get bigger and bigger on high frequencies. That's one thing that you probably clearly can see from this plot. The other one is you see that the approximation is better in frequency domain than time domain, right? In time domain, even at higher orders like 5, you still do not see any step type behavior. You see more and more oscillations, which is, by the way, the next topic, right? But in frequency domain, you see the matching is better than in the time domain, okay? So that's another thing I wanted you to see side by side. Now, what's the problem of using higher orders? As I said, the problem is the transfer function that has a polynomial of order, let's say what, 6, 7, 8 in the denominator and 6, 7, 8 in the numerator. That guy has 6, 7 poles. And the fact is, as you can see, if you want, we can draw a root locus of that. The poles of these Padé systems are clustered. They are close to each other. And such systems in reality are going to be very sensitive to perturbations, and perturbations are sudden changes in the system that you cannot predict. And that makes the system to not be able to reject and work robustly with disturbances and perturbations. So in general, if you add an approximation with order more than 10, you should expect your system to lose its robustness and show kind of different behaviors. And let me show you that, since here I talked about this cluster thing. So this is the Padé approximation order 5, right? This is the denominator, and this guy has 5 poles. So let me go ahead and show you this one. Okay, and these are the poles, as you can see, and you see they are kind of all close to each other, and the zeros are on the other side. Okay. So the system shows the behavior of non-minimum phase, of course, which it is because it is approximating a delay, and these poles are close to each other, and basically the higher the order, the closer this area is going to be covered by a lot more poles. So the poles are going to be closer and closer to each other, and this is what we mean by clustered poles. So in general, we don't want to go with very, very large orders because that reduces the robustness of the system. So what n is good for my system? If I want to approximate a system, what n is good? Well, the answer is this. It depends on what range of frequencies will your system work in, right? If your system only works up to, let's say, 4 radians per second or something, right? So let's say I predict that this is the range of in which my system is working, or let's say this is my cutoff frequency, right? Or the maximum frequency, depending on which range of frequencies you are using for this design of the system. If this is the cutoff frequency, then maybe if you look until that frequency, which order is good? Well, clearly I see order 3 is good, so I use only order 3, because after that I don't care about, right? I'm not going to be dealing with higher frequencies, then I'm not going to work in this region. Okay, I only work in this region, so maybe order 3 is enough for me. Okay, so you can look at the range of frequencies in which your system is working, and based on that you choose the n. And so once that's the case, then you can always approximate the system. So in this case, for example, let me show you this last thing before we finish the video. So if somebody says, this is my system, it is this original system that has 2 seconds delay, either because of transport delay or there is sensor delay or anything, right? Then I approximate this system with what? You see the order is, the delay is 2 seconds. And let's say I decided based on the range of frequencies of my system that order, let's say 3 is good. So I say what? I say numerator and denominator, this is equal to Padé of, and this is t and n. So your t is 2 and your n is 3. The order is 3. And then I say the Padé system equals transfer function of this numerator and denominator, right? And then my system approximated is what? Is equal to the original system, which in this case is GD, or G actually. The system without that exponential is that original G, times what? Times this Padé system, right? So instead of this system, I use this one, which is the product of what? The product of the original system without delay and a Padé third order. Multiply them together, and so this 5th order system is going to approximate the 2nd order system that has a delay of what? 2 seconds, because here we chose order 3. So hopefully this video was useful to you, and I could tell you about this important approximation that we use in analysis of systems with delays, and explain why and how to use it. Thank you so much. I will see you in my next lecture.